So it's been really a very nice conference, and I enjoyed it a lot. And I have to, I think, first bring a disclaimer that this talk has nothing to do with ZULF. And if I could opt for something, it would be stronger magnets to make things more feel stronger and also, or reduce weight on the instrumentation. So I titled this Some History, Thoughts and Limits, and knowing me a bit, essentially, this doesn't somehow, wait a second, change. Now, this will be about permanent magnets. So maybe this is in this conference because we have similar interests. So we want this mobile NMR to happen because it might be less expensive and still does the job, or because the sample can be not moved or without destroying it into standard equipment. So that could be large objects like the Earth, buildings or art, something valuable, archaeology or something like that. And of course it can go to extreme places because it is mobile, factory floors, outer space, whatever. And the special version of MRI, this could be used as a kind of point of care instrumentation that could be used in ambulances and so forth. And it is, of course, a challenge. And for as much as I'm concerned, it is also a lot of fun. I bring up this slide because I want to show you that this actually works. And during this lockdown in this corona pandemia, I was able to bring most of my equipment to my home and do NMR in the basement and finish some projects without much of a problem. This is one of the big pros in this respect. But for that, of course, it has to have a length scale that is really, truly transportable. I mean, portable NMR sometimes is a bit, if you screw some wheels under your NMR, it's already portable. Well, this is upper picture is a truck here. Can you see my mouse? That is a truck that was equipped with a superconducting magnet to support some less developed areas in the US, I think, with MRI. And this is an instrument by Katsumi Kose, weighs 200 kilograms to image fruits. And this is, of course, something more portable, the NMR mouse. But I don't want to restrict it to this length scale or weight kind of concept because this is a bit maybe too shortcoming. But the main weight or size and maybe problem in transportation, of course, comes with the magnets. And in that respect, permanent magnets are much nicer than electromagnets because they're very strong. You don't need to supply them with power. They don't need cooling. And of course, they are very interesting in terms of price, weight, and comfort. However, they have some problems, which is, for instance, since they're permanent, they don't have a time dependence and you can't switch them off, and that sometimes is a problem. A direct comparison, I mean, 1 cube of permanent magnetic material, iron-neodymium boron, to generate the same kind of magnetic field with a coil. Now it depends a bit on if you put in a lot of wire in this volume or very thin wire, you don't need that much current, or very thick wire, you have less resistance, but you, of course, need much more current. In the end, if you calculate the power that you need, it's about 2 kilowatts to create the same field as this permanent magnet. And another feature that scales, however, with this is also the inductance. So if you want to change the field, which will be in the later parts of that talk, the inductance might be a real problem because then you need a strong voltage and, again, high power to do that. There's also Moore's law of permanent magnets. So in recent years, the magnets became stronger and stronger. With iron-neodymium boron, we approaching sort of the theoretical limit of the remnants, that is some kind of 1.6 Tesla. And there are dysprosium magnets nowadays, which might become even stronger. So there is some increase, and of course the technology in other fields has also driven this development. Another nice feature about these very strong and very hard magnetic materials is that you can essentially use them, like I wrote here, like Lego bricks, to build the desired flux by superposition. And there's often this comment that you have to also consider the coercivity. That is the point in this curve where an external magnetic field sort of cancels the flux of the magnet, so depolarizes it. But for these materials, this is around 3 Tesla roughly, and the remnants, that is the other point on this axis where that is left when the external field is brought back to 0 after magnetization, that is about 1.5 Tesla. So as long as you do not create systems that create locally fields in that order of 3 Tesla, you're safe, and you can just treat these magnets as if they're independent and they do not really interact with each other in terms of depolarization or repolarization. And when you come to the geometry, there is essentially 2 different options. You can build a single-sided instrument, which is nice because you can just put it on the sample. And of course, you might also be able to surround the sample, then you have much more design features. Problem with the single-sided NMR is, well, you can play a lot of tricks in terms of how to shape the field, let's say parallel to this orange line, which should be the surface here, where you bring your magnet to, but you can't really do much about the decay in the perpendicular to that. You can shape that, and they're more clever and elegant designs than others, but in the end, you can't avoid decay, because in the end, it's all dipoles that you place here. And whatever the decay rate is, then it is definitely negative. So it's no way to bring that up again except placing another source on the other side. So that would be the surrounding issue. So that is essentially the concept of this NMR mouse or similar devices. And that idea here is that you create flux inside an object due to a strong magnet, and then you resonate a region where this flux fulfills the resonance conditions of RF sent in by this coil here. And this gives you essentially a very thin slice, because this is such a strong gradient, which you can then move through the sample either by changing the frequency or by moving the whole sensor away from the surface. And there are various ways of doing this, and different instruments have been built. And here is Bernhard Blümler showing the size of one of those little devices compared to a big instrument. This is all kind of interesting in terms of application, but as I said, you can't do so much about the design features here. That's why I come to the second part, and this is definitely dedicated to this person, Klaus Halbach, who invented these magic rings, and I'm going to tell you about that for the rest of the talk. Actually, they shouldn't be called Halbach magnets if it's the point of invention, because they were first suggested by a person called Mellison. Don't know where he lived and what else he did, but Halbach was the first to really build such devices and also come up with a general theory and a real instrumentation for that. And this was also due to the invention of rare earth magnets. So the idea here is that if you take a magnet or many magnets and put them in order here so that they show in the different directions, you get flux coming out here in circular direction or clockwise direction and anti-clockwise direction here in yellow. And so you can create a pattern. And now the idea is that you bring in another magnet array, which is facing each other, opposing each other, so that north is showing north and south. And then you see how these fields add up on one side and cancel on the other. And if you bring this into, this is a kind of conceptual design, but if you bring this in a more, let's say, scientific concept, then this is the case if the magnetization changes in the material continuously as a wave, like a wave here, and of course then is a wavelength associated with this. So this is what I would call a single one-dimensional Halbach array or Halbach system. And that is, for instance, observable. Maybe you have it at home in some fridge magnets if they have these kind of stripe patterns, but also magnetic foils are polarized this way. Otherwise, they couldn't be wrapped up. And if you now take one of those wavelengths here and cut the material to that wavelength and wrap it all around, you come to a structure that we call now a two-dimensional Halbach cylinder. In this configuration, it's a dipole. It also has this kind of dipolar pattern here of the magnetization. And if you then rotate this structure around its pole, you come to a three-dimensional feature or this kind of equivalent of this design, which I want to call the Halbach sphere. And there's more to it because this concept can be, let's say, generalized. So if you have a magnetization vector in the material at a position angle theta, so at a position theta, the magnetization points at an angle alpha, then if this angle alpha is an integer multiple of theta, you can come up with all sorts of polarities of this internal or external field depending on the sign. And twice this k gives you then the polarity. So +1 gives you an inner dipole, +2 an inner quadrupole, 3 inner hexapole, and so forth. So that is really nice, and we use that in physics in our department quite a lot. So this was a dipole, and at higher orders we use that for storing, for instance, neutrons or tritium and so forth. And there's also a general theory. I don't want to explain these equations here. I just want to show that you can calculate this all, and this is nothing you have to simulate or so. This is just very straightforward to do so. So these magnetic bottles or traps for particles, they have the nice feature that they have a very steep magnetic field at the wall, and inside there's essentially not much field. It's very flat because it has a very high order. Okay. But there are also some other concepts I just want to mention because it might be important for designs, because typically or quite often these magnets are confused with coils. A Helmholtz coil, of course, would produce a flux perpendicular to its winding, while the Halbach structure is created inside or transverse to the axis. And then the optimum distance for homogeneous field between them is given by a different distance, theoretically, for a dipole feature. And if you want to make a gradient, it's again a different distance. And then we come to the problem of actually making these structures. And I don't want to talk too much about this because that would be another lengthy talk. How to really, because you can't imprint this kind of pattern into the material at the moment. There is no coil that can do that, at least I'm not aware of it. So you either have to make it out of discrete segments that are parts of a cylinder or identical pieces which have some advantages, or wedges, or even more complicated structures like this here. Reason for that that it's a problem comes with two things. First of all, it's the deviation of the material itself, which is very inhomogeneous. It's becoming better, but somehow it also depends on what shift made the material in the production line. So here we probably see two batches of a magnet deviation in the remnants, otherwise identical magnets, and with 600 magnets we've measured individually to sort them later. And they also have a strong temperature dependence, which you can compensate, but this is again another lecture. Originally, we used these magnets because they have no stray field, and so they can bring them directly next to a superconducting magnet. And of course, if you want to make homogeneous magnets that produce a homogeneous field, you go for a dipole, which is the case, for instance, in this Macritech instruments, which are wonderful. shimmed systems down to some ppb resolution, or you combine these, for instance, for imaging, having a dipole and the graded field, the constant gradients of a quadrupole, to generate an imaging system that then simply has to be only rotated to create projections at different angles, which then could be reconverted in principle to an image using back projection. So this is the work from Larry Wall's group in MIT, and there's also work from Andrew Webb in Leiden, who did something similar, but he used gradient coils, so it doesn't use a quadrupole feature here. You can, once we had this task that we had to image actually or measure at a bottleneck of a sample, in this case a plant, so you really want to go to the narrowest path of that. And so the question arose, can you actually open these Halbach cylinders? Well, the forces in these structures are tremendous. I mean, maybe if you played with these magnets, they are really powerful. And they can go easily up to several hundred newtons. And so you have to be careful when assembling that. But yes, since this is a dipole, it's not exactly a dipole feature as such, but it's the field of a line dipole going through here in the center. This resembles the same, but it has the same zero at the magic angle. So we all know that from solid state NMR, that this is the zero of the second Legendre polynomial. And so you can open it at this position without any force. And we've chosen an angle close to that, 45 degrees instead of 54, but it's close enough. So we could build structures open and close, and you can put it around a plant, do imaging, measure flow, measure the water uptake of this plant during light and dark periods, and study that. So that is nice, but it becomes really handy when you want to use this structure, because it is not only a nightmare to assemble, but also it has a problem once you build it, how to access it, because it's all surrounding all of the sample. Well, you can open those as well at certain angles, which are a continuous kind of feature of this. So you have various options to open it at different thetas, at different phis. So there's the solution for that, theta versus phi. And then you can, in principle, nobody has done this so far, produce this, for instance, as a MIS tool where the sample is static and the magnet rotates, like in some very beautiful experiments that were presented originally by Dimitris Secularu, who did the same by superimposing a Halbach with a so-called Aubert magnet to put the magnetic field vector also at this magic angle. Okay, this brings me to maybe the most interesting feature of these Halbachs, and this is, since they don't have a stray field, you can easily put them into each other, nest them, so to say, and rotate them without having too much of an interaction between the rings, because on the outside, this is not a magnet. At least that's true for dipoles. So that gives you the option to have two extremes. When they're both parallel, you have the full field of both rings adding up. And if they have geometrically produced the same flux, you can also completely cancel the flux. And this is nice because this solves this problem, that you have no time dependence and control over the magnetic field with permanent magnets. And we use that, for instance, to build instruments to sweep the field mechanically. This is an instrument I built together with Gunnar Jeschke at the MPI and polymer physics in Mainz. And we did EPR with this and swept the field with a permanent magnet ring to do some indoor experiments and so forth. Recently, we also used that to counter-rotate them both at the same speed, the same kind of idea, which gives you then one static component which oscillates with this frequency, and that gives you access to AC fields. And that was used, for instance, in this apparatus to measure polarimetry with a Faraday effect. Yeah, so this is the field. It can generate a very strong AC field with decent frequencies up to some kilogauss. Sorry, and frequencies are also here it's only hertz, but it can go up to some 100 hertz. And finally, this has also much interest in magnetic particle imaging, but I'm only mentioning this. This is a completely different technique, but it's very interesting. Finally, something non-NMR, which I find quite fascinating. The magnetic force we all know of these magnets is tremendous, and some people want to use this to guide particles or robots, so forth, through the organs or through the body. And the problem there is that you cannot really guide with permanent magnets. That's a kind of common sense in this community, and it's also written in many textbooks, because what happens is the so-called Earnshaw principle, that if you bring a permanent or magnetizable particle to the south or the north pole, the force, which is the gradient of the magnetic moment and the flux, is always the same, independent of the orientation, because the particle either is magnetized by this magnet in the direction of its flux, or it rotates because it's so small until it is in this direction. And then, of course, you lose the sign of in this expression, and it's always attracted towards the magnet. You all know that everyday life experience, paper clips are attracted equally from the south and the north pole. And we had the idea, which is very similar to MRI, that we superimpose this whole situation with a very strong magnetic field, which is homogeneous, so that this particle or smaller thing here is always oriented along the stronger guiding field here, and then, or directional field to orient it. And then, of course, you can shift it away or pull it towards you, depending on the gradient you use then for steering. And you can, of course, create such a system then with Halbach rings. So if you just have one ring of a dipole to create this orientation field and another quadrupole to create a force, you can rotate the force inside this ring. And if you use a second quadrupole, you can even scale the force. And with that, you can then really write with these particles. So here's an example of a little steel ball in one of those machines, and it can even stop, like seen here, stop here, change direction. So that's really neat, and not only works with a big steel particle, but also with 75 nanometer nanoparticles, and people working in this field are excited about it. And because you can change the gradient in such a system, you can also use this, of course, for imaging, as very much as shown already by Larry Wald. So you can put an object in there, and then this is, of course, it's not really an experiment. It's just show that I have a brain. Okay, so this brings me to the last part of it, that this is only valid, all these kind of superpositions of gradients and magnetic fields, that you only create one component and have a single direction of the force or of your imaging modalities if the gradient and the distance of this point here is much smaller than the B0 field. Then it's a minor perturbation of this field here, and you can treat this gradient as a vector. And this problem is called concomitant gradients. And this happens a lot when you run then in the situation that we have here, that you have very strong gradients. And this is at the moment a real problem in this MPI business, where we want to build an MPI scanner that also can do imaging. Because originally this gradient field that you produce, of course, is a full tensor, and the assumption that you can only take the Z component of this field, for instance, for imaging, is only valid under these conditions, that this expression is much bigger, that B0 is much bigger than the gradient times the space coordinate. And if it's also constant, you can write it in the usual way. And if you don't have that, your resonances lie on circles, and they have a radius given by the ratio of B0 and G, and the origin also lies on a different point in space. And so this situation where you have two dipoles and sweep the field through this, make this line sweep up and down due to sweeping the field here, doesn't give you straight projections. And a similar problem also already was addressed by Larry Wall's group. One way to solve that, and I think Matthew Rosen in the next talk will also address that, is then, for instance, use additional encoding using RF encoding by gradients or larger arrays of gradient coils, of RF coils. Well, I skipped that because I think that went out. Well, yeah, you can make them big. I don't. I cannot do that, but some Chinese people can do this, and they make big magnets of 1 Tesla and 10 tons. And you can also make them very small. So this is a magnet I made for Dima Butker's lab, which is about 1 centimeter in size, and the magnets have 1 millimeter. And I don't know what field it produces, but usually we use 3D printers and magnets that you can buy inexpensively from the internet to make these devices, and they produce about 100 millitesla in a gradient of 1 to 2 Tesla, or something in this regime per meter. Really strong gradients if you need them. You can, of course, make them smaller. And I hope that this one day would also open the possibility, and this is an initiative by Lukas Winter to an open source imaging platform to make this kind of technology more affordable for the third world or the developing countries. And with this, I want to thank all the different places I've been through my career. Particularly want to thank in this respect Mike Mallet, who introduced me to magic rings at that time, or Halbach magnets, for the first time during my stay in Canterbury. Of course, I want to thank Bernhard Blümich and Hans Spies and Werner Heil, who all been my kind of colleagues and mentors, and really enjoyed a lot to work with them. And of course, I have to also thank the German taxpayers, because they pay my salary and my research. And I want to thank you for your patience. Thank you.
Thank you. That was an exciting talk. We had some questions. So Malcolm asked, what is the limitation on making Halbach arrays very small?
Not so sure. This morning I had an idea that in principle you could just run a wire through a magnetized ring of magnetizable material and put a big discharge over that to essentially imprint this kind of pattern into that. And not sure, I want to try this, but I need a big capacitor for that. I first have to look for that. And that might be possible, but if that works, I think there's no real limit other than Weiss domain or magnet domain as a building block of these devices. And of course, making this very small Halbach for Dima's lab was already a nightmare with my very clumsy fingers, and it was a nightmare. So you need somebody with maybe a piano player or so who can do that, or some other very sophisticated instrumentation I do not have. But in principle, no. Weiss domain is the answer, I think, to your question.
Thank you. So let's move to the next question. Quentin asked, you have shown that you have managed to open the magnetic cylinder and do NMR with it. Have you already done the same with the magnetic sphere?
Say what? What was the last part?
Have you done the same with the magnetic sphere?
Sphere?
Yeah.
No. This is something I suggested to Dimitris, but he had already different plans, and I'd never tried to build it. I just wanted to say that this is an interesting feature and nice instrument, and in principle it should work, but I haven't tried it. And I must get much more bored than at the moment that I will try to do that. It's a nightmare.